Hello students, welcome to Inside Physics. In this session, we will discuss what is a compound microscope. So we all know in our previous class discussed about a microscope. A microscope is an optical instrument used to magnify the objects which are very small and very inconvenient to see with the naked eye. So almost they are invisible to the naked eye, like some objects like viruses, bacteria, and which are called microorganisms. So in those cases, we need to magnify the image or size of the object to see them very clearly. So we use some magnifying lens in our homes. Generally, we see some small letters with some magnifying lens. That is called a simple microscope, already discussed in our previous video. So that single lens which is used for as a microscope here used two times, that is compound microscope. Compounding means increasing multiple times. So what we are increasing, the magnification is increasing multiple times by using an extra lens. So here in this diagram you can observe there are two lenses called objective and eyepiece. This is of small aperture and this is of large aperture. So objective is in front of an object which is nearer to the object, where we place the object and observe the image, and the eyepiece is nearer to the eye. So where you can observe in some clinical laboratories, they actually view the microorganisms through some microscope. The lens nearer to the eye is called eyepiece, and the lens nearer to the object is called objective lens. So what we are going to do with this kind of arrangement, we only calculate the net magnification. That means how many times the object is increasing its size. Magnifications means what? Increasing the size, the image size, the final image size. So when we increase the image, it will appears clearly. Okay. So we will calculate. First of all, there are some terms here you need to understand this diagram. This is the object distance u, and this is focal length of the objective lens. That means a parallel ray coming from this object is actually go through a point called focus. This is the focus. So this length, this is focal length of this objective. And again see here, this is the focal length of the eyepiece. Here see, the image is actually forming exactly on the focal plane or just around the focal point of this eyepiece. If you consider this point as a focal point, focal length, focus of this eyepiece, then the image formed by the objective is exactly on the focus, that means in the focal plane, or exactly nearer, very near to the focus. I'll tell you why. So if you are putting an object here, the image will be formed on the other side of the convex lens, and here the image is, this is the object, AB is the object, A dash B dash is the image of this lens. So this image is a magnified and inverted and real. Real magnified inverted image is formed here because of this lens. So this image is actually an object for this lens. This image is used as an object for this lens. So when you are considering this as an object, and see the rays are coming on and falling on this lens, and obviously because it is a converging lens, the rays are here passing through like this. But you can observe these two rays are not converging, they appear to be diverging, right? In this case the image will be virtual. That means to form an image we need to have a converging point of two light rays. So these diverging rays, they actually converge at a point exactly other side of the lens. That's why the final image A double dash B double dash is a virtual inverted magnified, very largely magnified image. Okay, So this is how the magnification is compounded in this microscope. First of all, an object, and this is the image of this object. This image is working as an object for this lens, and the final image, this object, the image for this object, the image is created right here, and two rays are converging backwards, and this is only the imaginary rays. That is why the image is virtual. Even the virtual image, we can see it clearly because the rays appear to converge at this point. So you can see the magnification, how the object, here we have put a small object of height h, and the height here, if you consider this height as h double dash, it's very large. H double dash will be very large compared to height of the object we have taken. So we have succeeded in magnifying the object number of times, n number of times. So this is the theory of compound microscope, and we will go to the mathematical form now. So for this lens, first consider this lens, the magnification. How to calculate the magnification of the objective, m naught, we say it m naught. So the magnification means we will consider it as tan beta. This theory we have already discussed. So here the angle beta, and this angle is beta, this is also beta. When you consider tan beta, opposite side by adjacent side, so that means h dash by L. I will write h dash by L. What is L here? See, I will tell you, L is the microscope length, or we call it as tube length. What is that length? The definition of that length is the distance between the first focal length of the objective, second focal length of the objective, and first focal length of the eyepiece. Listen carefully, the distance, tube length or microscope length L is nothing but the distance between the second focal length of the objective, that means this point, and the first focal length of the eyepiece, that means this point. This is the length. This is the length, we call it as tube length. So that is what I have written here. And if this is angle beta, this is also angle beta, then we can write similarly opposite side by adjacent side, opposite side h by adjacent side f naught, focal length of the object. In this sense, exchanging the terms, the magnification h dash by h, we know that magnification is the ratio of the image size by object size, then this will become L by f naught. This is the linear magnification of the object h, AB. Then we found out the magnification of the object lens. Now we see the image is formed at the focus of the eyepiece. Then what happens? If the image is exactly at the focus, the final image will be at infinity. If the image is exactly nearer, very near, not exactly at the focus, very nearer to the focal plane or focus, the final image will be at near point. We call near point as the distance from this lens as capital D, that is least distance of distinct vision, which we consider for a healthy human eye, it is 25 centimeters. Okay, so D, least distance of distinct vision, it is 25 centimeters. So the point B double dash will become a near point, and then we consider the magnification for the eyepiece. Magnification for the eyepiece, if you consider this as a simple microscope, we have already derived that formula, 1 plus D by Fe. This is for linear magnification when the image is formed at a near point. Okay, and when the image is formed at far point, image is formed at infinity, this equation will become like this. This is at infinity, when the image is at infinity. So how this became 1 plus D by Fe to D by Fe, we have already discussed in my previous video, simple microscope. So this is the magnification. Now we cannot call this as linear magnification. When the object is at infinity, we take it as angular magnification. So this is linear magnification, this is angular magnification. Okay, we consider that the image is formed at infinity. Image is formed at infinity. So in this case, what we will do is, see, the image will be formed at infinity. Now we calculate the resultant magnification. What is the resultant magnification? Resultant magnification will be, okay, we know that for a combination of lenses, resultant magnification will be m0 into me. So what we get here? m0, magnification of objective lens, L by f0 into magnification of eyepiece, this is D by fe. This is the resultant magnification we get for the compound microscope. To understand it better, we will see a numerical example. If you consider the focal length of the objective lens f0 is equal to 1 centimeter, focal length of the eyepiece is 2 centimeter, and the least distance of distinct vision we already know it is 25 centimeters, and if you consider the tube length or microscope length as 20 centimeters, if this is the data you consider, what could be the magnification we will get? That means with this formula. See, if you substitute these data 1, 2, that means 25, see 25, sorry, tube length 20 into 25 by 1 into 2. So here you will get 250 centimeters. Okay. Now it is not actually, you consider this as a magnification is considered in not any units, it is only the number of times the image is magnified. What is the resultant magnification for the data? 250 times. So this is how, this is, you call it as magnification of the compound microscope. Okay. So this is how we understand the theory and mathematical form of compound microscope. In the next session, we'll discuss one more interesting topic.